Okay. So, hi everyone. This is Vaibhav Nakrani. I've been an applied researcher at a startup, and thank you, Mr. Vivek, for giving me this opportunity to speak at the webinar. Mm. So, we'll be going over this paper. Leave no context behind. Infini-attention from Google Research, and whatever we have a problem right now with AI systems. We do not have enough context length, and that is the reason we employ RAG and everything on top of transformers to give them better context. So this paper addresses that question heads on. So yeah, let's get started. So what is the motivation behind the paper? Uh, According to Google, memory serves as a cornerstone of intelligence. It enables efficient computation tailored to specific context. Yeah. So if we have memory and if we have a good enough context, the transformers are really good at those tasks. So that is one of the main motivation behind this. Second, the attention mechanism in transformer exhibits quadratic complexity. Now, what does that mean? Quadratic complexity means uh, when you increase the context length, the complexity increases exponentially. Yeah. So the computation required increases exponentially with the context length from the transformer. Um, and the memory footprint is really high as well. So we'll go through what it is done for reducing the computation, but it requires more memory. This is an example of it. It requires three terabytes of memory for a 500 billion model with a batch size of 512 and a context length of 2048. This is, 512 batch size and 2048 context length. That is very small compared to today's standards. So even for that, you require 3 terabytes of memory of GPU RAM. So that is quite high. And it has been very difficult to serve longer context models because it is very costly to do that. So what they have presented is a compressive memory, which maintains a fixed number of parameters to store and recall information from. Yeah. So that is what they proposed. So we'll go over the vanilla attention first. So we can do two things with the vanilla attention. Now, the first is you can compute everything. So this is what it is. You have this sequence and you compute this one. You predict this token and you have this sequence. So what one thing you can do is you can compute everything out here and predict this. This goes into this one. You can predict everything out here. You do the computation all over again, and you have this token, right? Uh, this increases the computation quite a lot. So what we do nowadays is we have a KV cache. So that is the key value cache. And what we do is when we compute these attention scores, we cache it into the memory, and we predict this thing, and we just add this little entry into the KV cache, and then we move forward, and that is what we move ahead with. Yeah. So there is two problems with this. For the first one, where we compute everything, where we compute every attention score, the computation is quadratic in nature. So meaning it will increase exponentially with increase in context length. And for the second part, where we do the KV cache, we cache these values because they're going to remain the same. They will not change. These values will not change. And yeah, so when we do this KV cache, uh, the memory will increase linearly with the context length. So it will be quite a lot, the memory. So this is an example of someone who is really interested. This is the actual formula of calculating the KV cache memory. So for a small enough model that is 30 billion parameters, that is normal for these days. The model size is 60 gigabytes. The KV cache for a sequence length of only 1024, and that is quite small for today's standards. And a batch size of only 128 is 180 gigabytes. So that is quite high. That is three times the model size for only storing these key value key value matrices. Yeah. So, so if someone is interested in calculating the memory, this is how we do it. Yeah. So let me introduce you to Infini-attention. So what this paper does is it incorporates a compressive memory into a vanilla attention mechanism. So we have two attention. We have the standard scale dot product attention, and then we have a compressive attention. That is you can think of it as a hidden state, similar to an RNN. RNNs have a time step. They have a hidden state, and this is the same thing that they have done. So what we do is we store the old key value states in a compressive memory instead of an ever increasing memory. So we don't increase the KV states. We don't increase the KV cache with the increase in context length. We keep it fixed. This KV thing is fixed. Suppose if we have a 2048 sequence length, then the KV state will remain 2048 for the entirety of the training. So you don't have to increase the KV. Yeah. And then we retrieve these values from the memory by using the current attention query state. So whatever we are passing in the query from the current attention, we will retrieve the key value pairs uh, from these query states by matrix multiplying this with the older key values. Yeah, so that is how we do it. And finally, the long-term memory retrieved values and the local and the scale dot product at the current time step and the memory from the previous time step is combined, and then we have the final attention. So yeah, so this introduces very minimal changes to the standard SDPA, and it supports plug and play continual pre-tuning. Uh, it introduces minimal changes to the standard dot product attention, and it supports plug and play continual pre-training. Now, what does that mean? Now, that means that you can take any pre-trained transformer, and you can plug in this extra thing, and you can increase the context length of the transformer. And they have done it in this paper as well, and they have got some good results on this one. Yeah. Uh, so yeah, this is basically it. You can grab a pre-trained transformer, pre-trained model, and adapt Infini-attention to it. So this is the high level diagram of how it is done. So you have the QKV. So the QKV is the token that is split into three states. One is the query, one is the key, one is the value state, and we get the KV from this state. We have the query from this state, and we do the standard SDPA, the scale dot product attention, whatever we have the standard thing, and we retrieve. And this is the key values from the previous step. We multiply these queries from the current state, and multiply with the previous key values, and we get a compressive memory, and we concatenate them, and we concatenate. This is all basic. Yeah, and then we do sigmoid over here. So what does the sigmoid do? We'll come to that later. So this is the high level of what the new attention will look like. So yeah, how it is done. First of all, this is the standard dot product attention. You take the query, you take the key values, you transpose them, you get the QK. You you normalize it by the dimension of the model, and you multiply it with the vector. You get the softmax. So these two QKs. So this is what the attention score is, right? So this will give you sequence length by sequence length matrix of the attention scores. So yeah, this is what the main attention score is, and this is the final attention, by the way. Yeah, and this is the intermediate attention score. This is the main thing, and we multiply with the value, and this is softmax. So our goal is to store the bindings of keys and value states in compressive memory and retrieve them using the query vector. So we have this query vector from the current state. So we will call the query key and value states as the hidden states from now on, because they are actually hidden states, and they are very similar to hidden state in an RNN. So you can think of it as transformer combined with an RNN, architecture of an RNN. So that is what they are trying to achieve over here. So this is how you update the current memory. You get the previous memory if you have one. If you don't have one, you calculate it using this thing. So this is the current key values. This sigma, this is not sigma, this is not sigmoid. This is the ELU activation function. It is a activation function like ReLU and everything. ELU activation function plus one. You do it plus one, and you multiply it with the values, and that will give you the current memory. This will give you the current memory, and you add it to the previous memory, and that is how you update it. If you don't have a previous memory, if it is a first sequence, if it is the first token, then you just initialize it with a register buffer in PyTorch. If more technical people know that, you can register a buffer actually in a model. So this will register a buffer in it. So you don't have to keep track of the things. Yeah. So, and we have two hidden states. This one is the memory hidden state, and this one is the normalization hidden state. And this is calculated as the sum over the key values from t is equal to 1 to n, and you activate it by the ELU activation function again plus 1. Yeah. So this is normalizing constant in the equation, and it is the same thing. You update it the same way. You get the previous values if you have them, and you just add it to them, and that will give you the current normalizing constant. And this is how the calculation of the final attention. This is how it is done. So we talked about retrieving the memory from the query. So this is what they call retrieving from by the query. That is, you take the previous hidden state, the ms minus one. So this thing, ms minus one. This will be the previous hidden state. Yeah. So you take this thing and you your matrix multiply with q. This is also activated from the ELU plus one activation function. So you do this for both of the hidden states. This is the memory state, and this is the Z. This is the normalizing constant. If you can tell the normalizing constant because it is basically a sum over the values of the key matrix. So this is how we do it, and this is the final A memory that we get, and this is what is new in this paper. Yeah. So the final attention is sigmoid beta. Now this beta is a learnable parameter. So this is only the single learnable parameter in the model added. There is nothing else that is added as a learnable parameter. Only the beta is learnable. So what does this beta do? So beta is kind of a gating function. You can think of a scalar or a single value that gates the memory. What does it have to attend to the A memory, or does it have to attend to the A dot? You do 1 minus sigmoid of beta so that it sums up to 1, so that the entire attention sums up to 1. So that is the reason you do sigmoid of beta and 1 minus sigmoid of beta. But yeah, the main motivation behind the beta is you get a single scalar that is learnable, and that is what will tell the model should the model attend to the previous memory, or should it attend to the current attention, or to the previous attention, or should it attend to both. Yeah. So this is what the beta is about. So yeah, the benefit of this model will be you get an unbounded context window with a bounded memory footprint. So what does that mean? You get infinite, basically infinite window. You can just pass in any number of sequence, and it would get, hopefully it would retrieve the most important parts from the whatever we passed in. And we have a bounded memory. We don't have an exponentially increasing memory or exponentially increasing computation. So that is one of the main things that the paper has put forward. And yeah, so the constant memory complexity, that will be the memory complexity will be only the D key by the D value. So suppose you have a 1024 sequence length. So the D key and D value, the dimensions of key and the dimensions of value, that will be a matrix of 1024 by 1024. So that is the only memory we require. We don't require with the previous memory. That is the only thing we require for this one, and plus the D key. So this D key comes from this thing. We have to plus this thing because we have this hidden state as well. So that is a constant memory complexity of this. So this is the only memory that we are adding to the model and nothing else. And for complex context, MS and MZ. Yeah. One thing to keep in mind is this is applicable to each attention head in a single layer. So if you have 8 attention heads, you'll have 8 of these things. You have 12, you'll have 12 of these things. We usually have more than 8. We usually have 12. It is in multiples of 3, I think. Yeah, it is 6, 12. So yeah, so you'll have one of the attention memory for each of the head in a single layer. So that is one thing to keep in mind. The memory is different for each attention area. Uh, so what they basically achieved is they achieved more than 100x compression than the previous methods called memorizing transformers. So this was the previous method, and it was not constant memory, it was not constant computation. They had some caveats in it. So yeah, so they achieved 100x more compression and achieved better perplexity. So perplexity is a measure of uh, assessing a language model. It's not perfect, but yeah, it works. The perplexity works uh, because if you wanted to assess a model, you have to take one model, you have to take the second model, and you have to run it through various tests, and that would be not feasible. So that is the reason we came up with perplexity. So for the interested one, perplexity is basically the um, the cross entropy loss raised to the power of exponentiated by e. So that is the formula for perplexity. Yeah.
So, folks, if you have any
So
questions, you can ask because it's a complex topic with the mathematics as well. So, if you want
yeah,
something
yeah,
to
yeah, yeah.
feel
Please
free
ask.
to ask
Please ask.
our audience.
Yes, yes, definitely. Please ask if it's not clear.
And yeah, I think there's mathematical algo, so it's good to go slow. And if audience wants to ask anything, they can ask.
Yes, yes. I can even rewind the slides if needed. Yeah. And okay. So should I continue? Yeah. Okay.
Yeah,
So
yeah.
okay. Yeah. Perfect. So this is what they came up with. Mm, this is the compression ratio. The transformer Excel. This is quite old. This paper. It was 3.7x. Memorizing transformer. It's 1x. RMT 73x. And the compression ratio here was memory size was 114x. So yeah, and this is the average token level perplexity. So this is the perplexity scores of sequence length of 2048, and yeah, they've done quite good with this, and yeah, lot of difference. 13 and 9 is a lot of difference for perplexity.
So, what is
Even
perplexity? What is perplexity?
Okay, yeah. So I'll explain perplexity. Perplexity is we need to have something to assess these language models. So we can do it. We can't do it extrinsically. That means we can't compare this model with this model and run various tests on it and come up with we have a test set and suppose we run it. We can't do that. So this is an intrinsic uh, evaluation method, perplexity. So this is what we have come up with. It's not perfect. No one says it's perfect, but it is good enough. Yeah. So that is basically the cross entropy loss raised to the power to e. So that is what we came up with perplexity, and
Higher
it
the
it was
perplexity, higher the accuracy, or is the other way around?
no. Lower the perplexity, better the model. Yeah.
Okay,
So
okay.
that is the perplexity. This perplexity thing is quite old. I think Claude Shannon, who derived the cross entropy, who derived the formula for entropy, she came up with this perplexity, and we are still using it. Yeah, we haven't found a better way to assess these language models. She was working in 1985, I think, for Bell Laboratories, and she came up with perplexity, and we are still using this. So yeah, that is some history on this one. Okay, so one interesting thing to note was if we go back, remember I called this the gating function, the sigmoid of beta. It tells you this will give you a scale, this will give you a percentage like 0.3. You obtain 30% of the previous memory, you obtain 70% of the current memory. So for an example, yeah. So this is the scalar value. But one interesting thing that they found was the gating mechanism emerged with two types of heads. One with specialized heads where the scores were close to 0 and 1. So what does that mean? Close to 0 and 1 meaning if some of the gating functions had 0 scores, like they did not want to attend to the previous memory, and sometimes the score was 1, so they wanted to attend to the entirely to the previous memory and not to the current attention. So that is what that means. It's a 0 and 1. Yeah. and and the other head was a mixing head, and that is uh, your 10 to half of this attention, your 10 to half of this attention, and yeah. So these are the two gates that the model came up with after training, 0, 1, and 0.5. So this is quite interesting. Yeah. So let's get to the experiments. So they trained a model from scratch for 1 million length passkey context retrieval. I'll explain what is passkey context retrieval. And they trained another model for 500,000. 1 million length is basically you're retrieving some information over 1 million context. Yeah. And the other thing is they trained this model was trained from scratch, and they trained another model with 500,000 book summarization. The 500K is the length of the book, and the basically the model is to summarize the book. And this model was continually pre-trained from a trained language model. So this was extended from a pre-trained language model. So yeah, they did both of those. So what is the passkey context retrieval? I'll explain it. The passkey just hides a random number into a long text and asks the model ask the model to get it back. Yeah. So in 1 million length of context, it will have a random number in it, and the model has to retrieve that random number from the context. Yeah. And the book summarization is the model's goal is to generate a summary of an entire book, and I'll explain how the summarization is assessed, the how good the summarization is assessed. I'll explain it when the slide comes. So yeah, so this is the thing. If anyone has any questions, please ask me. Happy to answer. Okay. So so these are the results for the zero shot, and these are the results after fine tuning the model on 1 million length passkey. And the infinite transformer, the zero shot was not good enough, and after fine tuning for 400 steps. So this is they fine tuned on basically they pre-trained a transformer, and then they fine tuned on 5,000 length inputs. So this is what the fine tuning is, the 400 steps. So the zero shot wasn't quite good, but after fine tuning it on 5,000 length inputs for only 400 steps, that's quite small, not that big. uh, it's basically 100, 100, 100. Yeah, it's basically retrieving this passkey from this 1 million length context. Most of the time it's 100, 97. For 1 million it goes down quite a bit, 94 sometimes. But yeah, for a language model, not bad. And this is the root scores. So these are the scores for the book summarization task. Basically, the model is given a 500K length book of token size, and it is asked to summarize the book. And these are the Rouge scores. So what is a Rouge score? Rouge one meaning you assess, you have uh, you have the model summary, you have the human summary, and you assess based on the n grams. So one is unigram. You calculate the unigrams, the similarity between the unigrams, that is per token, per token calculation, how single tokens are similar to each other. The Roach 2 is bigrams. You take two words from the model summary, and you take two words from the human summary, and you just measure how many of them are similar. Right? So that is what Roach 2 means. And the Rouge L is you find the longest subsequence in the in the in the model summary that matches the human summary. So you take the longest string basically from the model, and you just you get these. So these are the precision scores. Precision recall, everything is combined in this one. You have everything in Rouge, so they've basically combined everything and given a single score for this. So one thing to uh, really focus is uh, they 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 compared the model against an encoder decoder transformer. So these are really good at summarization. Encoder decoder transformers are really good at summarization, and the model was good, was way better than these part and everything. And yeah, the sizes were the small as well for the models. So this is it. So final thoughts on this one. uh, can this be considered as an internal RAG implementation since the gate value settle at 0, 1, or 0.5? Either the model is attending to the previous memory, or it is taking entirely the current attention score. It is just mixing both of them. So can this be considered an internal RAG implementation? Yeah. So the technique introduces basically infinite context with bounded memory and compute. Can actually scale to a million length input sequences. It is a plug and play module, so this is really interesting. Since it is a plug and play module, one can really extend smaller models and have a really good context window for them. If the RAG is not working, if external RAG is not working, this can be done because the fine tuning steps were uh, from here. If you can see the fine tuning steps of 400 steps. So yeah, that's not much of compute to fine tune a model. So it is basically plug and play. It has promising results across various benchmarks. And yeah, they already came up with a better implementation like name transformer spam, which combines ring attention to this. So yeah, Miss Vivek sir always tell the goalpost in my we don't know where do we kick. So this is what that means. Uh, this thing they already came up with a better thing. Yeah.
I see. Okay, so is that it, Vaibhav?
Yes, that is it.
Okay, so I know it's a little heavy duty for an afternoon, but good stuff, Vaibhav. So lots of algorithmic details. We love the maths of it. Audience, any questions for Vaibhav here? I know just one or two questions in chat if you can check. Maybe
Okay.
more of a discussion. I think it's more of a discussion. Let's just check the chat. If you have any comments?
Okay, so Bhavani Shankar, so perplexity is kind of LLM model. Yes, it is. It is a model evaluation technique. Basically, everyone uses perplexity as of today. Most of the models are assessed on perplexity. So yeah, that is thing. And one real example, an example of perplexity topic clustering, where you have some yes, you can use perplexity, but yeah, topic for clustering. For topic clustering, you have different metrics as well. You can use perplexity, but perplexity is basically for language modeling. Uh, if a model is predicting the next thing, so that is where perplexity really helps. Yeah.
Okay, great. So, audience, any other final questions? So, Vaibhav, nice presentation. So, lots of algorithmic details. And as I said, we love the maths. Have to,
Yeah.
review it with some fresh mind. There is a question from Minal. You can check in the chat.
Yes. What are the parameters for measuring perplexity? Can you please explain unigram, bigram, and n-gram metrics? Okay. So the parameters for perplexity is basically whatever the cross entropy. So Mrinal, do you know about cross entropy scores of the last layer of a model? If you know that, so perplexity is basically
Hi, Vaibhav.
yeah.
Are you saying cross entropy in general, or like the formula for
Yes.
cross entropy, or?
No. I'm not talking about the cross entropy, but do you just know what is cross entropy? Because it is a loss. It is some kind of loss.
Yeah,
Yeah.
it's
Yeah.
a loss, right? Yeah.
Yes. So perplexity is basically that raised to e. That whatever we get from cross entropy raised to e, and uh, we don't have much intuition about it. I tried to gather some intuition, but I was unable to found any good intuition about perplexity. But from various experiments, they found that this thing sort of works as a proxy to measure the quality of a language model. Yeah.
Okay. And the unigram, bigram, and n-gram metric. Can you please show that slide again?
Okay.
Just
Yeah.
want to
This
see.
one. Yes. This one. The Rouge one and the Rouge two and the Rouge L metrics.
So, what is
So
Rouge
these
L actually? Rouge L is any number.
No. Rugel is the most common string, the longest common string between the summary from the model and from the human
From the
written
human.
summary. Yeah. So that is the
Okay.
most the longest string that we have, and these scores are basically the F1 precision recall. You can just I did not mention it, but these are basically the
Yeah, I was
number of
wondering, is
words
that
matching.
percentage or is that
No, that
percentage
is
or
this is not a percentage. This is the metric, and it is gathered from the precision recall and everything. The Rouge one you can look it up, and it's fairly easy. It's not that hard. It is
okay?
this
And
one is a
overall,
unigram.
what does the
This is the
overall
bigram.
mean? Overall,
Okay, overall this one.
yeah.
Okay, so we have one more metric as well. That is a Rouge L key. So I think the overall is that one, Rouge L key, or this can be a weighted overall. I haven't looked into the overall scores. I've looked into the Rouge one and Rouge two and Rouge L. But I think we have four scores from Rouge: one, two, L, and Rouge L key. So the Rouge L
Okay,
key is Rugel matches sentences by sentences, and Rugel key, matches entire paragraphs by paragraphs. You can have overlapping sentences. You can have unfinished sentences as well in Rugel key. So I think the overall is a measure, but this is a Google's paper, so uh, they don't say that much. This was quite hard,
okay,
doing this paper. Yeah.
okay. Thank you.
Yeah, you can look it up. I think it's not that difficult. Rouge one and Rouge two.
What is this
Uh,
paper? Which paper is this?
it is Infini-attention. Leave no context
Oh,
behind.
right. Okay. Fine,
I'll
cool.
I'll show you. I'll show you the this is the you just type this. It is
Leave no
this
context
paper has
behind.
been quite famous. Yeah, it has
Okay,
been quite famous. You can find
okay,
really good
okay,
things on this one.
Earlier, there was
okay.
no, you only need attention. Now you got to leave no context behind.
Yeah.
So they keep
Uh,
coming up with, some
I
interesting
think I
catchy
think I,
phrases.
yeah, I think the Gemini 1.5 Pro might be using a variant of this thing, but we can only speculate as of this point, because it had some really good capable recall capacities. If I remember the 1.5 Pro, whatever they released, I think it's not released, but they have the API accesses, some of them. So yeah, it had 1 million context context retrieval. So I think they might have implemented this in some fashion.
Yeah.
So,
There's some
whatever, don't
comment by
mind.
Sai. Yeah, go ahead.
Can you explain the passkey again? A little bit
Which one?
lost. Passkey. But
Passkey. Okay, yeah. Okay, this one. Yeah. So this is a task. This is basically a context retrieval task. The passkey. So what they do is you take a 1 million length token size and you just hide random numbers in it, and the model is asked to get the number back by prompting. So this is what the passkey is.
so it's like a masking.
No, it's not masking. You hide a number in this long context. In 1 million tokens, you hide a single number or multiple numbers, and you just ask the model to get it back. What was the number? That is what you ask, and it gives you back the number.
The number is nothing but the embedded value, right? You mean to say?
Number is you can just type in any number in your text, and you can ask the model to retrieve it, and it should retrieve it. Yeah. You don't have to do anything. You just type a random number in between, and you just ask the model to retrieve it.
Didn't get it properly. Yeah, let me get some-
I think Sai is just summarizing this algo in a note in chat. You can check that.
Yeah.
Meanwhile, audience, any other questions? So I try to understand it, but I did have some difficulty because it was fairly
Actually,
intricate.
sir, I had a quite some difficulty understanding this. There was this really cool gentleman on Discord that helped me understand this paper. So yeah, they haven't given much information, but the Discord community is really good. Folks can go to Elither AI Discord, and people will help.
And
I
Vaibhav, there is no sort of a GitHub code for this, as a demonstration, is there?
Yes, I have GitHub codes as well. if
Okay.
someone has to look into it. I can share it.
Yeah, you can put the link here in the chat.
Yeah, I'll do that.
There's a question also on blue score or rogue score. Which one is preferred? Root score.
Okay,
Root,
so I have a root score is for summarization. Blue, I don't think I recall what was blue for, but
yeah,
rouge
blue
is for
is for
summarization.
measuring accuracy for NLP tasks.
Yeah, that might be. But for summarization, I think rouge is quite good because it matches the n grams, 1 gram, 2 gram, and
Yeah.
yeah.
Okay. Any other questions, folks?
So I'm a little bit out of context, but do we have any standard um, kind of evaluation which to do when, which kind of evaluation method to use? Like some Sai mentioned, blue for translation, rope for some tokens, for summarization and all the stuff, right? Some standard prediction or something of that. Any good
Yeah.
article or a paper?
Yeah, there are metrics for specially designed for all these tasks. For summarization, you just have to basically go towards Luge, and you might have some others as well. For language modeling, most of them do perplexity as of today. Whatever papers I have read, most of them do perplexity. Yeah, so that is a good proxy, I think, for language modeling as of now.
Okay.
The metrics are really important in this one because metrics is what will tell the model is good or not. Yeah.
Okay, that brings us to the end of this presentation. Thanks a lot, Vaibhav. Interesting session.
Yeah.
And good to see
Thank
your
you.
research and deep dive, study into these topics. I
Yeah.
would look
Thank you.
forward to more of these webinars from you in this case. Thank you, audience, for joining.
Yeah. Thank you for the opportunity. Thank you. Bye, guys.